Canonical fields, self-supervised learning of post-canonicalized neural fields. The application of neural fields, that is, coordinate-based neural networks that implicitly parameterize signals in visual computing, has led to remarkable progress on various computer vision problems such as 3D scene reconstruction and generative modeling, leading to more accurate, higher fidelity, and more expressive solutions. In this paper, we present Canonical Field Network CaFi-Net, the first self-supervised method for category-level canonicalization of the 3D position and orientation of objects represented as neural fields, specifically neural radiance fields. During inference, our method takes as input neural radiance fields of object instances from a category at an arbitrary pose and estimates a canonical field that is consistent across the category. Now we will dive deeper into the various aspects of our work. Given posed RGB images, NeRF and its variants learn a neural network to synthesize novel views of complex scenes. While NeRFs excel at fitting a single object instance or scene, it struggles to generalize to object categories partly because objects can be in arbitrary 3D poses. Thus, some methods have used pre-canonicalized datasets such as ShapeNet and ModelNet 40 to circumvent this problem. This inductive bias aids category-level generalization in problems such as 3D reconstruction, but limits the application of neural fields to such datasets and makes it difficult to adapt to data in the wild. We can also use these datasets to formulate canonicalization as a supervised learning problem. However, our goal is to canonicalize without using manual pose labels. Recent research has shown that self or weak supervision is sufficient for learning pose-canonicalization on images, 2D key points, and point clouds. None of these previous self-supervised methods can operate directly on neural fields. To the best of our knowledge, ours is the first. Canonicalizing neural fields is challenging because unlike 3D point clouds or meshes, neural fields are continuous, noisy, and hard to manipulate since they are parameterized as the weights of a neural network. While our method is aimed at NeRFs, it can be extended to the 3D post-canonicalization of any neural field. Unlike 3D point clouds, rotation equivariance in fields is more involved. Here, we show a simulated 2D vector field to demonstrate the challenges involved. Rotating the field shown here requires two operations. First, updating the positions of vectors in the field to new rotated positions, and second, rotating the directions of the vectors. Thus, to address the challenges associated with neural fields, we extend the notion of equivariance to continuous vector fields and show how networks for processing 3D point clouds can be extended to operate directly on neural radiance fields. CaFi-Net takes as input a sample density field from a trained NeRF model for a given instance. CaFi-Net is designed as a Siamese network that contains layers to extract equivariant features directly on vector fields. Densities alone do not capture the position and directional components of the field, so we use a combination of densities and gradients of densities at query locations of the grid as our input signal for CaFi-Net. The gradients of densities do not violate the equivariance property. You can refer to the paper for more details. To canonicalize for rotation, we leverage equivariance properties of spherical harmonic functions to obtain rotation equivariant learnable features on the field. To promote our method to learn only from occupied regions and to counter noise in the density fields, we weigh each equivariant feature type by its density. This weighing has no effect on the equivariance of features. We hierarchically aggregate features at resolutions 1/2, 1/4, and 1/8 to obtain global equivariant features and compute its dot product with point-wise spherical harmonics to obtain a pose-invariant embedding. We use a linear layer on top of the pose-invariant embedding to estimate grid coordinates in the canonical frame. We then choose the best canonicalizing transform and penalize it for canonicalization. We use the canonicalization laws to self-supervise our learning, where we transform the predicted canonical grid coordinates to the input grid using the canonical rotation and compute a point-wise L2 distance between them. The orthonormality loss forces the predicted equivariant transformation to be orthonormal, while the Siamese loss penalizes for consistency between different shapes belonging to the same category. During inference, given a previously unseen NeRF model of a new object instance in an arbitrary pose, our method estimates the transformation that maps it to the canonical field. There was no publicly available dataset large enough, consisting of sufficient instances to train our model, which is why we first developed a synthetic dataset of 1300 NeRF models across 13 categories using Blender. For each category, we pick 100 instances from ShapeNet, rotate the shape randomly, render 54 omnidirectional views sampled in a cube around the shape using Blender, and finally use these views to train 100 NeRF models per category to obtain a total of 1300 trained NeRF models. During both training and inference of CaFi-Net, we use a uniformly sampled grid of the trained NeRF density field in the object's bounding box as input. We have shown a few example NeRF renderings on the left and an example 3D visualization of the gradient field for the bottom right chair on the right. Here, we show a few results. On the left, we have the renderings from the input NeRF fields, and on the right, the rendered canonical fields from our method. We clearly observe the consistency in the orientation of the instances across a category for each of the 7 displayed categories. We designed experiments to compare our method with 3 3D point cloud based canonicalization methods, namely principal component analysis, canonical capsules, and Condor. Our method performs well across all categories with low variance between different categories. To have a fair comparison, we train the above methods on point clouds sampled from NeRF scenes for points on and within the object. On average, our method performs better than point cloud based methods in the CC and GEC metrics and is on par with the state-of-the-art method Condor in the IC metric. We conduct additional experiments to justify key design choices in our method. The average canonicalization error over 4 categories on all 3 metrics is lower than when using gradients as compared to using density XYZ locations as the input signal representation. Next, we observe that weighing features by density turns out to be better than weighing features by the local average density, as the local average smoothens out details that are necessary to canonicalize the volume. Finally, although our method can canonicalize even without the Siamese architecture, it makes it easier to learn over instances in a category as observed in our results. Our approach has limitations that future work should investigate. First, we require a 360-degree NeRF model of objects and cannot handle partial views from front-facing NeRFs. Second, canonicalizing densities with uncertainty is more difficult as the uncertainty increases for very thin or small structures that can be missed as seen in the case of watercrafts. Furthermore, we also inherit the issues that TFNs have with symmetry as seen in the case of monitors here. These issues need to be explored and resolved in future work. Here, we show a few more results from our work. We clearly observe the consistency in the orientation of the instances for the 6 categories displayed here. Here we show the acknowledgements for our work. Thank you.